Hello everyone, I hope you are doing fine. Let's go back to our exercises on dynamics. This one here is based on dynamics from Meriam. I guess it's the 7th edition. Maybe you have the newest edition, but I could not find the newest edition. So this one here is the exercise from chapter 1, the first exercise of chapter 1. So you can have a glimpse of a better design than this one. But I will put the right design, on just here on the left after I finish. So what we have here, you have something like a circular disc with a radius of about 16 meter that rotates about a fixed axis through point O. The point O is here with an angular properties of W2 rad per sec and an angular acceleration of 3 rad per sec square. What we want here, we want the instantaneous value of the velocity at A and the acceleration at point A. So let's go for that. The first thing that we can see here, we have the center. I will not say the center, but we have, I didn't draw it well, but we say that the fixed point O is not aligned with the center of the circular disc. The point O, which is a fixed point, is kind of offset of a distance of 3 of R quarter from the medium line. So here we can start working on to find the velocity and the acceleration at point E. So let's go for that. The first thing we are going to do here, since we are working with dimensions that are not aligned, it's better for us to work with vectors. So vectors. It's better for us to really work with vectors. So what we are going to do here, I'm going to write to first identify as this fixed point here as the origin of my new axis. Instead of putting the axis x and y here in the middle of the circular disc, I'm going to put them here just aligned with the fixed point O. So from here, I will say that the point O, its coordinates are OE plus OJ. And the point A, I will say that is R quarter E minus RJ. Then you can see it from the vectors. You can see that from here to here we have R quarter, and then from here to here, or better, from this horizontal line to the point A, we have the distance minus R. So that's why if you look for the coordinates of the point A and the point O, you find the point A as the coordinates R quarter E minus RJ. So from here we can compute the vector OA, which is this vector here. So we have it like R quarter minus 0, so it's R quarter minus 0 E plus minus R minus 0 J. So I take this one and minus this one. So we have here R quarter E minus R J. So we have it. Since we have the radius, we have the coordinates or the radius of the segments OA, and we also have the angular velocity, we can compute the instantaneous velocity at point A. So we can use the formula. We can use the simple formula. The velocity at A is the dot product, not the dot product, but it's the vectorial product of the angular velocity of on the circular disc with the the vector OA, which we just calculate. And this one will be E, J, K. Here, input it will be 0, 0, 0, 0 minus W, and then we will have R quarter minus R 0. I'll do some calculation here. After I do some calculation, this is a nice technique that you have. I don't know if you know this technique to compute when you want to compute the vectorial product, but I use this technique. I just forget how to call it, but it's a really awesome technique. So we have 0 here, and then we have minus W R quarter J 0, 0 minus which would be plus, and then so we have minus, and then minus, so we stay here minus WR E. So here we have the expression of the instantaneous velocity at the point A. So if we substitute with the value, we'll have like 2 like 16 quarter J minus 2 dot 16 E, which leads to minus dot 32 E minus 1 is 2, and then O dot O. Here it's E, and then here J. I made quite a bit of confusion. So this is here, as we see it, is the instantaneous velocity of A. The instantaneous velocity of this point A here. What we can compute now is the instantaneous acceleration at the point A. So for that, we also know this, that the instantaneous velocity, especially when we have a circular disk, the instantaneous acceleration will have two forms to calculate. We have the transversal acceleration, which can be computed as the vectorial product of the angular acceleration and the vector OA. And the angular acceleration, we see that the angular acceleration, it goes in the anti-clockwise, the anti-clockwise direction. So it's positive. Meanwhile, the angular velocity goes to the clockwise direction. That's why it's negative. So here we have. We have 0, 0 alpha, and the OA, we already compute the OA vector. I'm just going to reproduce it here. So we have R quarter minus R 0. If I do the same proceeding that I did earlier, what I will get here, I'll get like R alpha quarter J plus R alpha E. So I'm going to substitute with the numerical value. I will have here something like that 12J plus that 48A. This will be the transversal acceleration. We need to compute also the normal acceleration, which will be something like omega, the vectorial product of omega and omega r, which here we know as the velocity of the instantaneous velocity of A, which we compute earlier. So here we have this one. We have O minus W, and the instantaneous velocity we compute it here. I'm going just to reproduce it here down here. So we'll have minus W omega r minus omega r quarter 0. So after further review and further computation, I will have here something like omega square omega r E, J minus square omega R quarter E. Here it's E, and here it's J. So after substituting all the numerical, all the later with the numerical value, we have here DAX 64J minus DAX 16A. So from here, I will have this one. I will say that the instantaneous acceleration is the transversal acceleration, the tangent acceleration, plus the normal acceleration. And we know that the transversal acceleration, we compute it as this one, and the normal acceleration, we compute it as with this value, which leads to the value of that 76J plus that 32E. So with it, we can conclude that with the small steps that I showed you right now, we can compute the instantaneous velocity and the instantaneous acceleration. I hope that you enjoyed the video. Don't forget to subscribe to my YouTube channel to follow for more video about dynamics. See you next.